Hi, my name is Robert. I work on the GPU acceleration and Matter Labs. Basically, me and my colleague Michael, which is also watching, we are working on the GPU part, all the GPU side code, and also work on the integration of that code into our proof system. Dog name is to the Boojum. Boojum is our proof system, and the goal of the talk is basically walk you through it, how it works, and what we did to implement it on the GPU, what we learned, some comparisons to basically the first implementation and what we currently have, and yeah, some hopefully interesting information. For the agenda, I will start with the overview, basically explaining give you some information about the proof system itself, and then I will go on and explain how the workflow of proving a single circuit looks like, what kind of operations we do there, in what order, and that should give you a feel for kind of the complexity and how many operations we need to do to produce the proof. Then we will discuss the building blocks in a little bit in more detail, what we have on the GPU side. Those are the blocks we use to kind of compose the proof workflow. And then I have point 4, how it started. This will show you basically how a profile of a whole GPU proof looks like, yeah, then I will go a little bit into detail. There are certain parts which I will kind of zoom in on and explain what's happening and what we can see kind of from the profile, and basically what would be needed to improve on this first version. Then next we will come to current state. So this is more or less the state in which the prover is currently. So then there we will see the performance difference between the first version and the current one. You will see where the improvements have happened, and again we can zoom in on certain parts to explain better. And the last part would be future improvements, what we have in the pipeline basically, and we already know what we can sort of expect in terms of performance improvement. Okay, so Boojum overview. This is just a quick overview to give you some general information.
What does Boojum
mean? Boojum is a creator from a poem. I don't know, the author is Carol. I don't know, it's some famous poem. I don't remember the name. But the point is, it's described as the scariest snark in, and so that was. Come again?
It's from Alice in Wonderland?
Yeah, I think so. Yeah. Yeah. So that's the name. So, but Boojum is kind of a general name. It means multiple things, and one is the name of our Rust-based library. This is the CPU implementation, you could say, implements the basic types and basically all the components needed to define circuits and also do things like witness generation and proving and verification. So this single library could be used to basically perform proving on the CPU. So the Boojum itself uses Plonk-style arithmetization. Some call it Plonkish. It's using custom gates, and I think people know it from other proof systems like Plonky 2. The second important part is the Frye commitment scheme. So we are using hashing, Merkle trees, and the Frye to commit and then do openings and basically prove the correctness. Efficient witness generation. We do some directed graph analysis to kind of parallelize the witness generation. So it's fairly quick. Usually this part is not well parallelizable, but we are aiming to make it about as quick as the proof itself. Then there is the extendability. Boojum is written in a way which allows for someone to take it and basically define their own custom gates and their own circuits and use the rest of the library to basically then build a prover and so on. Single stack. The library itself is part of a stack, and the other parts I will mention later, which is the GPU proving part. But the point is that we are trying to kind of deliver all that is needed for GPU proving, and not only CPU but also GPU. Boojum itself, like the library, is already open sourced, and the GPU part will come shortly. It's not yet open source, but we are not far away. We need to polish it a little bit. Okay, so it's also the name of our next proof system. So I don't know how familiar you are with zk-sync or zk-sync era. That's an L2 on Ethereum. It currently runs with our previous proof system, which was using also Plonk, but with KZG commitments and BN254 curve and so on. So this is the replacement for it. The goal of the replacement is to massively improve the performance, and this, like concretely, we need to lower the hardware requirements. Like the current proof system, for example, needs, like for the GPU, in terms of RAM, we need 80 gigabytes of GPU RAM. So that's basically limiting the proof system to only data center GPUs like the A100. So that's one thing, very limited selection of GPUs, which are kind of in high demand nowadays with the AI boom. And they are also expensive. So that's the second point. We will want to drastically lower the proving cost. Again, that comes kind of hand in hand with going away from these big GPUs and being able to be run on much lower spec GPUs. Another important point here is that we plan to distribute the proving. So, of course, in that case, we need to be able to run this on consumer hardware GPUs. So, basically gaming GPUs. The current version of this new GPU prover needs only 16 gigabytes of RAM with the option to basically trade certain or do certain recomputations where you throw away some memory and like some computation save on memory, but instead you at some later point you need to recompute it again. So there is a possible trade-off between memory consumption and proving performance. So theoretically we could go as low as 8 gigabyte or maybe even 6. Yeah, but it's at a cost.
Question. You mentioned there's a trade-off between memory and computation.
Yes, because
Can you explain it?
basically, take for example LDEs. You might need the same LDE in different places during the proof workflow, but if you don't have enough memory to hold all your LDEs during the whole workflow, you throw it away and then recompute later.
So can you cache some of these expenses?
Yes, that's like if we go for maximum performance, then we want to cache everything basically. And
Like can you do it like in a general way, or you have to? It then depends on the specific circuit, like because the constraints are different. So you have like a general framework which will identify.
Not that general yet, but that would be a goal for later. We are not that far. Like the GPU prover is maybe 2 months old by now, so we are not that far into optimizations and like making it more generic for other GPUs. Currently, we know we have 16 gigabytes and we work with that, and later we will add on this functionality where you can kind of tune it into working on a lower spec, like with less memory. Okay. And another interesting point is that this GPU prover already is running in production. So it's proving blocks on our mainnet, but it's running in shadow mode. It means it is producing proofs, but they are not posted to the L1. But we have tools to verify the proofs. This is done basically to battle test it. We want to know whether everything works as we expect, and this is the way to do it. Okay. So now let's talk about circuits. Let's say we start with a batch of transactions which go into one block. We form a block, and then the next step would be to compute a certain split into circuits. We have different types of circuits for different types of operations. The main circuit, the generic circuit, is called main VM in our case, but there are other circuits like Ketchak or circuits for memory and so on. And these circuits can then get aggregated into multiple steps until we arrive at the final circuit. So just quickly, base circuits are the circuits at the first level. Like I mentioned, main VM, Ketchak, other ones. Then we have leaf circuits. This is the kind of a second layer. They aggregate. They can aggregate circuits which have the same geometry, which means like the witness has same length and the number of columns is the same. So that's the leaf circuits, and then we have node circuits which are there to aggregate the leaf circuits. And finally, we arrive at the scheduler circuit, and this one is different. So all these previous circuits are basically like the ones, or they are the Boojum circuits with with Fry. Those we can say it's Boojum is a Stark prover. But the last step is different. Here we wrap the Stark into a snark. So before we post the proof to the L1, we kind of take the last proof, which is a Stark, and we have a snark circuit. And this one again uses our current proof system. It's just much smaller, much faster, and we wrap it and post it to L1. Okay, so now to the workflow. So this is kind of similar with what you do in Icicle with NARC. So we have something we call setup. This part is kind of a one-time computation we need to do before we can start to prove the circuit. The important point is that we can keep the setup on the GPU as long as we are computing the same proofs for the same circuit. And this is quite beneficial because the distribution of types of circuits is very uneven. Something like 70% of all our circuits for a single block would be just one type, the main VM type, and the other ones are just much lower numbers. So as long as you are working with the same circuit, you can keep the setup around and don't need to compute it each time. The setup itself is made up of transfer witness indexes from host to device. These witness indexes are a static thing for the circuit. They don't change. Based on those indexes, we generate a copy permutation matrix. This is quite expensive operation, probably the most expensive one among the setup steps. And then we do some transformation on the polynomials. In particular, we there are other polynomials aside from the copy permutation matrix, which come directly from the host. Stuff like constant columns, which are also fixed for a particular circuit. So we do some transformation using entities, like inverse entity and bit reversal. So they come in Lagrange form, but we transform them to monomial, and then do LDEs on them, depending. What the degree of LDE depends on basically the blow-up factor for Fry and for quotienting. So this is all cached, and then I will try to go quickly through this. Round one, this is just about witness polynomials. We move the polynomials to the host, do again this transformation. This type of operations you will see quite often. It's almost always the same. From Lagrange to monomial, bit reversal, LDE, of certain degree, depends on whether we do the LDE for commitment or for quotienting. Once we have the LDEs, we compute a Merkle tree in those areas and take a cap, so that's a certain level in the Merkle tree, and push it into the transcript, and the transcript will later generate the kind of inputs for the next round. This is basically the fiat Shamir part, where we push something into transcript does some hashing probably. I'm not really familiar with the details what's happening inside, but then you can pull challenges from the transcript for your next round.
And this happens inside the pushing and
And no, this part actually, so we compute the Merkle tree cap on the GPU and then just transfer the cap to the CPU, and like the transcript lives on the CPU, but it's very tiny. So the amount of data you need to transfer is very tiny. That's why we don't bother like making a special implementation on the GPU for it.
So LDE stands for?
LDE, a low degree extension.
Do you use it to what extent? How much you extend the polynomial?
Depends on the circuit, but for the fry, we only extend by factor of 2. But for the quotient, it depends on basically on the constraint degree of the gates, and we have either 8 or 4 depending on the circuit. But the main circuit, the most important one, uses factor 8.
If I translate LDE into polynomial operations, it's like, what's the cost of an LDE? It's like doing...
LDE is basically an entity with some little computation on the inputs before you do the entity.
You can say that it's right, like polynomial interpolation.
Yes, yes. So we end up after, basically, we go from monomial, do entity, and end up again with Lagrange form, which are like points on the domain we are using. Okay. Round 3, which is all about quotienting. This round we do coset by coset because these are expensive operations and also need a lot of memory. And also the blow-up factor is potentially 8, which means doing coset by coset you can kind of compute, throw away your temporary allocations, and then do the next one and so on. For each coset, we have special purpose columns and general purpose columns. Special purpose columns have kind of fixed gates. They don't need any selectors. General purpose columns work with selectors, and I think I skipped something somewhere in round 2. In round 2, we did the copy permutation argument and the lookup argument computation, let's say. Those computations generated certain polynomials. And now, during the quotienting step, we need to do quotienting also on those polynomials. But they are different from gates. They are kind of done through some arithmetic operations. And yeah, that's it. Okay, so once we computed the quotient polynomials for all the cosets, we can do inverse entity on the whole quotient polynomial, which is now, like if we started with 2 to the 20, domain size 2 to the 20, blow-up factor 8, so it's now 2 to the 23. That will be the inverse entity of that size. Then the output from the entity we split into chunks we know that they are small degree polynomials because they come from LDE, so that's why we can do it. Right, so they are here. They are in monomial form. We again, as we have seen before, just turn into do LDE and commit. That's it. That's round 3. And last round. By the way, these rounds, those are kind of arbitrary, chosen by me. I'm just choosing points where we do some always push things into the transcript, and that's for me is kind of like a synchronization point, but it's not exact. So, like during Fry, we were doing this multiple times, and so don't take it with a grain of salt. Okay, so round 4. We produce some polynomial evaluations. In our case, because we have those polynomials in Lagrange form, we use barycentric evaluation. Then we do deep quotienting, which is again it's a bunch of arithmetic operations, and then we end up with our code word, we could say, for Fry, and then basically do the Fry rounds. In our case, we tend to do 1 commitment and 3 foldings, so reduction by factor of 8. And in the end, we end up with some small output of Fry, which can be verified by the verifier.
Have you been able to parallelize any of the actual Fry stages?
Like the folding is parallel. Sorry. Yes, we can parallelize the folding. Like it's. You just operate on pairs of values, right? So like the fold itself is just reading 2 values and producing 1 value. Mm-hmm. And so, but it's really so tiny. So you only ever see any real like contribution to the whole runtime in the first Fry round, and after that it's basically gone. So that's one output from the prover for the verifier. Then optionally we can do proof of work grinding if we want to, but we don't use it currently. We have it implemented like with the Blake 2S hashing, but not in use for our current because I don't know if I say it correctly, but basically the security coming from those previous steps is sufficient, so we don't need to do the grinding. And and the last step is just perform queries, basically selecting certain rows from the polynomials and producing Merkle paths. And that's the last thing we produce for the verifier, and that's it. That's the whole proof. Right. So, what did we have here? So, I already mentioned the Boojum library, RAS library, but we have few more. We have, this is kind of, I named it CUDART sys and CUDART simply because that's the name of the CUDA runtime API. CUDART is basically just a bindings library. There is not much there, just to produce the bindings, and CUDART builds on top of that. It's a few abstractions, basically some nice wrappers and so on. Stuff for memory allocation, transfer set, then creation and usage of streams and events, synchronization between streams and events, and so on. Then we have kernel execution, where you can take a kernel and define the parameters for it and execute it. Then we have callback execution, which is what Kartik asked. When we need to do some CPU computation, like part of the workflow. This is done through, in CUDA it's called host function, but it's essentially a callback. But it's executed on the CUDA stream, basically. CUDA stream is kind of defines how the steps, like the dependencies and how the computation proceeds. Yeah, and then there are other abstractions, helpers. Then we have the Boojum CUDA crate, which contains basically those all the kernels we need. So the goal with this whole CUDA-sys and Boojum CUDA crate was to have the bare minimum of CUDA code or C code. So every higher level logic lives in Rust part. So the Boojum CUDA crate has a CUDA part and Rust part, and all the kernels live in the CUDA part, but all the rest lives in the Rust part. So we have functions like entities, inverse entities, bit reversals, Poseidon hashing. We have actually Poseidon and Poseidon 2. We use Poseidon 2 in production. Then Merkle tree construction, Merkle path queries. Then we have simple point-wise operations like addition, multiplication, subtraction, division, stuff like that. Then we have some specialized operations like barycentric evaluation, folding, partial product quotienting. Next part is gate evaluations. These are actually generated by a build script. We have gates defined in Boojum, and Boojum CUDA has a build script which takes this definition and generates CUDA code for it. So those are kind of generic gates, but we have also some special gate implementations. For example, for the Poseidon gate, because it's so complex that for one, it would be kind of difficult for the compiler to generate efficient code when it's fully unrolled. And also because we can do better than just taking what exists in Boojum and translating it. We have our own Poseidon implementation, which is better than what we could get if we just generated it from Boojum.
With the bit reversal,
Yes.
Do you actually like bit reverse things in the global memory?
Yes.
That's it, like
Yes.
like what would be the size of the vectors that you actually do this?
Well, we usually do it on 2 to the 20.
Oh, wow. And is that like how dominant is that in like your overall processing?
Not very dominant. But it's also not small. So currently, our entities, we have only entities which go either from normal to bit reversed or from bit reversed to normal. But we could use the Stockholm, I think, is the algorithm, which would preserve the order if we want. But we don't have that implementation right now. So
With the current implementation, you're
Kuli-Tuki,
forced to
yeah.
to bit reverse sometimes.
Current is Kuli-Tuki and
Right.
yeah.
Okay.
Okay, so where was I? Yes, gate evaluation. So that's a little bit interesting there with the generation. Then proof of work I already mentioned, and CUB functions. CUB is a library from NVIDIA for certain operations like scans, reductions, sorting, stuff like that. So, for example, we use sorting during the generation of the permutation matrix, or we use reductions, for example, when we do the barycentric evaluation, we need to produce single value. So, we just reuse some functions which fit to our problem.
So basically, you're staying inside the GPU except for the feature things, like for the.
Yes, and at the end there are like the queries. We need to compute the which queries to make. That's also happening on the CPU, but like 99% of the time we are just on the GPU. Okay, and then we have Shivini crate where the actual workflow, like the source code for the workflow lives. Shivini crate also contains, like the Boojum CUDA crate is sort of relatively low level. It's near to the CUDA API, but Shivini creates some abstractions on top of that. So stuff like allocators. In Rust, you can define your own allocators for vector, and here we can have allocators which allocate actually on the device memory, or can create pinned memory allocations. Then we have abstractions for polynomials handling, like basically all the operations you can do on polynomials. We have higher level abstractions to abstract away some of the details that are happening on the CUDA side. Then abstractions for other Boojum CUDA functions we have. Then the workflow itself, and this crate is still very much work in progress, so we will be adding more of those things.
So is this sort of like an interface?
Yes, like this crate is actually used by a service. That's the actual prover service that lives in some Docker container, for example, that runs in some Docker. And the crate has its own API, but the API is like, here is the witness, this is the setup, and out comes the proof. Okay, so how it started. This was the minimum viable product. So this was basically the first version we had that was able to produce correct result, correct proof. And now I am going to show you some profiler outputs. The performance. 6.6 seconds for a single main VM circuit. Just to give you an idea about the circuit itself, the domain size or the length of the trace is 2 to the 20, and it has roughly 160 columns. I don't know the exact number, but something like that. And to give you some idea how this compares to the CPU prover. Again, I don't have an exact number, and it depends on the exact hardware you use, but roughly 50 seconds or 1 minute, something like that, with multi-core CPU prover. And this time, so that's order of magnitude better, roughly. And this, we actually target quite small GPU. You could sell small in terms of how performant it is. It is the L4 GPU. Uses only 70 watts and kind of is actually intended for not for AI training, but for inference. We chose this GPU in particular because it has a good price in comparison to something like 8100, but still it's the latest Ada Lovelace architecture, and yeah, we hope it will be like the availability would be good for it, and it's cheaper. Like when we talk about price versus A100, it's depending on the concrete CPU you choose and amount of RAM, 4-5 times cheaper, roughly.
We actually have a couple of L4s in the lab, and we think it's actually the best in terms of this metric of the cost per proof or something.
Yeah.
So in a sense, it's not like we need to look at it as a whole, right? Like it's actually a very good GPU.
Yes.
Maybe the best one there is.
Yeah. Like before we decided which one to use, I looked over the like the prices and did some benchmarks, and the L4, in my opinion, was.
Are you only considering data center class GPUs?
No, because you could take like 4090, and that's probably twice as fast as the L4, at least twice.
But the 4090s are a lot less expensive, right, than L4s? Don't L4s have a certain, I don't know what the cost
like,
is, but I thought they were considered the data center parts and therefore were...
Yeah, yes, but for now we are just using data center infrastructure, so just Google Cloud basically, and
4090 is actually less, like even it's the same architecture, it's just tuned at a different operating point. It's much less power efficient than this.
Yes.
Yeah, right. Right, they go run at a really high clock.
Higher clocks,
So they're
yes.
much more expensive in power. They're cheaper in process, much more expensive in power.
Ah, okay, okay.
Okay, so 6.6 seconds. Also, another data point is our current proof system. A single proof on A100 takes something like 18 seconds, but it's not the same circuits, so you can't directly compare. In the new proof system, we need roughly 3 times as many circuits as the one in the old proof system. So, yeah, just to put things into perspective.
You run a single proof at a time? So this
On a yes, single proof per GPU, because you can, yeah.
You don't run...
No, because of memory constraints. We could kind of schedule them one after another, where there would be certain overlap, but so far we don't do it.
As far as we've already touched the maybe higher level. As far as the rollup, this proof is this is what gets basically checked back into
no.
L1, or this still needs to get aggregated?
No. Like this 6.6 seconds is for the first layer of proof or circuits. Like this is the main VM circuit, the most used.
And
because
still aggregate.
Yes, you need
these and create another like aggregate.
Yes,
proof, and that's what goes into
you aggregate
into
until you end up with single Stark, and then you wrap it into a snark.
Okay. So it is worthwhile if you can run
yes, because again, some concrete numbers. Our blog are usually something like 750 transactions, and in the new proof system, that block would be split into something like 2,000 circuits. So roughly, let's say 3 circuits per transaction. So you can start kind of compute from that how much a transaction costs actually. It's
So you'd need to like multiply this by 1,000 and then divide it, or 2,000 divided by 750 to see like really what the cost is of the transaction.
Yes, but you need to know the cost of the machine, which is
Right,
like
yeah.
like the L4, just again concrete number, like the with the lowest tier CPU costs something like 250 per month spot like spot
Around.
price. Yes.
Like power maintenance.
No, like to rent on from Google Cloud.
Alright.
So that's the spot price. So it's quite cheap actually, and yeah, we will see. So but okay, so 6.6 seconds, we put that into perspective, but we already knew this is okay
It's much better than what it was.
It is already quite a lot better than it was, but you know there is room for improvement. And now a little bit of profiler output. Okay, so this is a little bit heavy, but to give you an idea what we see here, this is the 6.6 seconds, and I marked the kind of the rounds here, 1, 2, 3, 4, and some little bit more detail about the operations that are happening there. And we also see here the split across the kernels, which kernels contribute how much to the overall computation. We can also see that the utilization is quite poor actually. Like lot of normally high utilization would be where this would be all blue, but it's not full, so not good. And these green and red chunks, those are host to device and device to host transfers. So we see also a lot of time is spent just moving data. Okay. Diving a little bit, I will try to go through this faster because I'm already talking too long. So round 1, we see a lot of time is spent just moving data. This also means this green color means that the memory from which it's moved is not pinned, which means it's rather slow, the transfers. And we do some entities and bit reversals here, and then we do LDE. Each entity is always two kernel calls because we can't do it in one. And then we see Poseidon plus this is also Poseidon. Just this is the leaves and this is the nodes of the Poseidon. Yeah, and we see also some memory sets here. That's about it. So transfer commit. Round 2, I kind of grouped this with setup because in the MVP, in the first version, we have this setup computations kind of spread over the whole prover. It wasn't grouped together. It was just there. We like no special care was taken to make the setup kind of a separate thing. So here we have transfers of the setup, like transfer, some transformation. And then we have computation of partial product. This is for the copy permutation argument. And for this one small is for the lookup argument. So what we see here already is that this is not very efficient. Like there are a ton of multiplications happening. Like these go into thousands. We don't have the exact number, but these go into thousands, and we have also a lot of additions, inversions. So that's basically what's happening in those argument calculations. But this is not very efficient. Commitment, we have seen that before. Not much there, like entities, Poseidon. It's just not small because the arguments are smaller in relation to the trace. In round 3, this is where the quotienting is happening, and here we see the split into 8 quotients. You see 8 repetitions basically of the same thing. Again, we see already here, I guess I can dive a little bit deeper. This is a single quotient in the quotienting. And what we see here is basically the LDEs, and then there are some gate evaluations, which actually take a lot of time, but for example here, evaluate Poseidon 2 gate, reduction gate, and so on. So there are parts which do the gate evaluation. And then we have the quotienting for the partial product, and for the, actually, it's not even there to see. There should be a quotienting for the lookup argument. But again, same problem as before. Ton of multiplications, additions. They're also very, very slow. Like it takes, you see, it takes 200 milliseconds just for single cosets to do this. So this is not good. And round 4, here, let's say, there are some evaluations, but then we do some transfers which are not needed. Deep quotienting, again, not efficient. Again, many additions, multiplications, same problem. Okay, and then we basically do the commitment, and then fry queries. Again, very inefficient because we are transferring data to the CPU and without pin memory and so on. And actually, there was fry part is this here, and these are just the queries. So this shouldn't be really happening here, but that's something that needs improvement.
Does all of this run on one single stream, or do you have?
Yes, like the first version is just a single stream. We don't even attempt to use multiple streams because all over the places we have these transfers which are not to pin memory. So you will get synchronization anyway, whether you want it or not. There is not much point to try to run something on a different stream.
The reason I'm asking that is if you put it into streams, you might be able to get 2 of these running at the same time and then overlap compute. And
right, but 2 of which, you mean?
No, I mean just all 6 rounds, unless it takes so much memory that you can possibly get 2 of these going.
No, for example, in the third round, the cosets, you need to really do this coset by coset because it needs so much memory.
There's so much memory that you can't have a second one.
No. Yeah, so that's the MVP. Current state, 2 seconds. Much better utilization. We still have some problems with transferring the witnesses and with setup, but the rest looks much better utilization. Yeah, round 1, not much improvement. Then I separated the setup here from round 2, which is much smaller now. Round 3 still the most intensive part because we do these 8 cosets, and for each we do the quotienting. So that's where most of the work is happening. And round 4 is actually tiny because that's where all the evaluations and fry is happening and fry queries. But we were able to collapse it to very tiny part. Yeah, this is not much change from before. Then we have the setup. only interesting thing here is all this is to generate the permutation matrix. So we do some sorting, some what's the name? Sorry, it doesn't come to mind. But there is an operation from CUB, and then generate the permutation matrices here. Okay, round 2, we were able to improve on it a lot. So the partial products much better now, but still we see not quite utilized fully. But it's only 48 milliseconds, so you know.
Question?
Yes.
Maybe you can elaborate on what was the problem and how did you improve the utilization?
Yes. So basically, we've seen this problem repeat over and over. It's the simple operations which we do, many of them. And the problem here is that we are working on the Goldilocks field, which is very small. The arithmetic is very fast. And the problem is, if we do each operation in isolation, we always load the data, do the small computation, and store data. So basically, we are just moving data in and out all the time. That's the problem. So what we need to do is to fuse it together. Write a kernel which fuses all these operations together, only loads data one time, does whatever needs to be done, and then stores the result. That's the solution for all of these problems where we see these multiplications and additions and so on.
So the problem was you had many kernel calls?
It's not a problem of utilization, well, to an extent, but the main problem is the memory bandwidth. You are just loading and storing again and again.
From global.
Yes, because the operations is very, very tiny itself. It's very fast. So you are just spending time waiting for data without computing. Okay.
So you got to exploit the data locality, right? If you don't exploit the locality, then
yes.
you lose.
And the L4 GPU has a relatively low memory bandwidth, something like theoretically 300, but in reality with error correction you get something like 250 max. So it's not great, and round 3. This is very nice. We got basically rid of almost everything that was problematic. Now it's dominated by entities and then basically partial product quotient and gate evaluations. This is zoomed into the single quotient. So here we see the LDE, then the gate evaluations, partial product, and lookup argument quotienting. That's it. So, or I can go a little bit. So these are the fused operations. We replace all these additions and multiplications with just these kernels. That's where the main saving comes from. Okay, round 4. Not much there. Barycentric evaluations. And then deep quotienting. Again, deep quotienting was problematic. Again, replaced with single kernel call. And then here is the fry part and queries. We've got rid almost of all the traffic that was blocking us here. So it's like 7 milliseconds. This is about the fused kernels I mentioned. Basically just repeating. Many sections are dominated by these simple operations, and it's problematic because of what those actually do. Just do this simple operation right and repeat again and again. So it's bad for scheduling. You are wasting a lot of CPU just to schedule these small kernels. and also bad because you have lower utilization, a lot of memory traffic. Better solution, writing a dedicated kernel. And yeah, that's it. I already explained that one. Yeah, this is an example of such operation. These are taken from the Plonky 2 paper. This is the copy permutation argument. I won't go into the details, but if you want, look it up. The point here is that we are replacing all these additions, product, division, all these things we are fusing into a single kernel. And this is how it looked before. This is the compute quotient. Like this is for the quotient, quotienting. Very bad, and now single kernel. And we did similar fusions for partial product argument, lookup. Yeah, I already think I mentioned all of this. So that's what it looks like now. We still have quite a few things in the pipeline. Pinning host memory is one thing to basically enable overlap, because unless you pin it, you will basically, when you try to schedule other operations, the copy from non-pinned memory will block. You say to CUDA, do it asynchronous, but it will block anyway. So that's a problem if you want to do some kind of overlapping scheduling. Right, so overlap will be lasting. Use of callbacks, we still don't have callbacks anywhere. Basically, we just synchronize, then do something on CPU, and then schedule the next step. But that is something we want to do. Again, more fusing. We've seen that there is still some place for improvement. Not as much as before, but still. Okay, then this would be something we want to improve our abstractions, because the abstractions we have now are not always, or let me put it this way, the goal should be for an abstraction to be equally performant as the lower level. But it's not always the case. Sometimes we have abstractions which kind of introduce some degradation in performance, so we want to get rid of that. So then there are some, this comes from the abstraction itself. Basically, there are some device-to-device copies which are not necessary, and also memsets. Removal of recomputations. We still didn't get rid of all of the recomputations. So we still have some places where we do them, but it requires a little bit more logic to basically cache and then retrieve and so on. Yeah, and then the separation of setup from the rest of the proof.
You mean that currently for every circuit it always loads the ones themselves?
Yes. Currently there is no we always do all the things. So that's the next step we want to do, separate it, and then we would have basically two API calls, one for the setup and then second one for the actual proof. And the last is CUDA graphs. I didn't research so far how much it will bring, but considering how many operations we are doing, there might be some benefit to it. And I think this is the last one. Here is an example of optimization of rundown. If you remember, it was something like 480 milliseconds, where we just were transferring data and then doing entity and Poseidon and commitment. This is a version which I have written in the Boojum CUDA API, a little bit lower one. because it can't be currently expressed in with Chivini, but goal is to get there. And here you can see I can basically transfer in chunks and overlap the entities plus partial Poseidon. What I mean by that is that although I have 160 columns I want to put into leaves, the Poseidon is absorbing at rate of 8. So I can basically do single absorption, compute a single round, a single permutation of Poseidon, and then store the state and reload it at a later point and continue. And this allows me to break up the Poseidons into chunks and overlap them with the transfers. So here you see the transfers, they are done here, and the rest of the Poseidons runs, and that's it. Yes, that's it. Thank you.